Hi everybody, welcome to lecture 9 of Electrical Engineering 331. This lecture will be broken into two parts. There's a part 9A, which is a continuation of ideas we have discussed before, and then there will be a lecture 9B, which will present some new ideas. Okay, so for this 9A, let me remind you that in the final example of lecture 8, we saw how to find the ramp response of a system from the step response. And then in problem 3 of test 8, which we discussed in a good bit of detail and for which I provided the solution and also a separate video, we found the response to a more general input. Once again, starting from the step response. That was the knowledge we had, was the step response of a system, and from that we were able to find the response to a more general input. Now, and as I noted at the time, that problem 3 of test 8 was actually problem 2.5D in your book. And we found that to be a fairly complicated problem. The ideas behind it were not all that complicated, but actually executing the solution required some care, and it was a little bit tedious. So here, what we will do is, like I say, that was problem 2.5D. We will here look at problem 2.5C, which is the same kind of idea, but fortunately this one is not quite as tedious. So let's see how this goes. Once again, as in these previous two cases that mentioned up here, what we start with is the step response of a system. And you will note that this step response is the same as we had in problem 3 of test 8. So here's our step response. But this time, what we seek is the response to this input. And if you look, you'll see that this input is different from the one that we had in problem 3 of test 8. So let's see how this will go. Okay, well, the first step is to express x of t in terms of singularity functions. And I hope that when you look at this graph, you can see that the first thing, moving from left to right, the first thing we see is u of t, and then that turns off at t equals 1, and we go all the way from positive 1 to negative 1. So that is minus 2 times u of t minus 1. And then we go back up 1 unit at t equals 2, and that's accomplished by adding in this u of t minus 2. So, so this is how we would express x of t in terms of singularity functions. So if x of t is the unit step of t minus 2 times the unit step of t minus 1 plus the unit step of t minus 2, then the response to x of t, which we will call y of t, is just the response to the unit step minus the response, minus twice the response to u of t minus 1 plus the response to the step of t minus 2. And I'll point out now why this problem will be less tedious than the one before. Notice that in 2.5D, or problem 3 of test 8, if you go back and look at it, finding y of t required knowledge of y ramp of t. That is, it required knowledge of the response of the system to the ramp function. But this input doesn't contain any ramps at all. It only has steps in it. And therefore, we don't need to know y ramp of t to calculate this function. Okay. So, y step of t, again, we've already said it, but I just pointed out here. Well, actually, I guess we did not say this, so let me explain in a little more detail. So we're going to need y step of t to find this output. Y step of t is given graphically right here, but let's express it in terms of singularity functions. Well, the first thing you do, you see, as you go from left to right, is you see this positive slope of 1. So that's r of t. Then we not only want to flatten it out, but we want to turn it into a negative slope of 1. So we have minus 2r of t minus 1. And then we want to flatten that out, and so we add in an r of t minus 2. So this is the expression for the response to the step function. This is y step of t. So you can see that we're, in some sense, almost done with this problem, because all we have to do now, the output that we're looking for, only involves y step function, but just at various arguments. So we just need to put this function together here for various arguments and various weights, and we'll be done. So let's see how it goes. Okay, so again, we're looking for y of t, so I'll put y of t here on the left, and it's equal to y step of t minus 2y step of t minus 1 plus y step of t minus 2, where y step of t is given by this. So this first line is y step of t. You can see the arrow here. The second line is minus 2 step of yt minus 1. You see the arrow pointing down here. And then the final line is y step of t minus 2. And so now let's look in a little more detail. Okay, the first line is supposed to be y step of t. And you can see that indeed this first line here exactly matches what we have for y step of t. Exact match there and here. Now, the second line, as we said, is minus 2 y step of t minus 1. So you see the minus 2 here. And now this is y step of t minus 1. And you can see that that's true. Just substitute in t minus 1 everywhere up here. So you have r of t minus 1 there, minus 2r of t minus 2 here, plus r of t minus 3 here. And then finally, the last term is y step of t minus 2. And so just plug in t minus 2 for t everywhere. R of t minus 2 right there. Minus 2. The t is replaced by t minus 2, so that's t minus 2 minus 1, or t minus 3, r of t minus 3. And then t minus 2 is t minus 4 there. So that's not too bad. And we already have arrived at our answer. And now what I'll do in the next line is just collect everything together. So we have an r of t here that comes down. And then notice we have a minus 2r of t minus 1 there, and a minus 2r of t minus 1 there. So that's minus 4r t minus 1. And then we have a r of t minus 2 there, and a minus 2 times minus 2, so 4 r of t minus 2 there, so 1 and 4 is 5, and an r of t minus 2 there, so that's 6r of t minus 2. And then we have a minus 2 r of t minus 3 there, and a minus 2 r of t minus there, so we have a minus 4 r of t minus 3. And finally, down here we have a r of t minus 4, which I bring down here. So this sort of complicated looking function can be expressed here in one nice, neat formula. And so now what I want to do is to express what that function is equal to over the different parts of the t domain. And we're going to go, as usual, from left to right. Okay. Well, this is a ramp starting at t equals 0. This is a ramp starting at t equals 1. This is a ramp starting at t equals 2. This is a ramp starting at t equals 3. And this is a ramp starting at t equals 4. So none of these ramps have started until at least t equals 0, and therefore, for t less than 0, all of them are 0. So y of t is equal to 0 for t less than 0. Now, as we move past that, as we get into the range for t between 0 and 1, just this first term has turned on. And remember, when it turns on, r of t is equal to t. Okay? Now, as we continue to increase t, and it gets now greater than 1, but still less than 2, well, then the first two terms will be turned on. So we have a t for the r of t term, and then minus 4, that comes down, and r of t minus 1 is t minus 1. So that's how I get this. And we'll simplify that in the next steps, but we won't worry about it now. Now, as we continue to increase t and it gets between 2 and 3, well, now the first three terms will turn on. Now, this term doesn't turn on yet because it doesn't turn on until we get to 3, and we're between 2 and 3 now. So the first three terms will turn on, but the fourth and fifth terms don't turn on yet. And let's see, what do we get? Okay, again, r of t is t minus 4. And notice each time we just bring down what we have from the previous step. So here we bring down 0, you don't even see it. But here the t comes down here, and then we have something new. And then t minus 4 times t minus 1, that comes down here, and then we have something new. And then this will all come down to the next step, and then we have something new, and then all of this will come down to the next step, and then we have what is new. So each time you're bringing down everything from before. So right now we're between 2 and 3, so we bring down this, we have r of t is t minus 4 times r of t minus 1 becomes minus 4 times t minus 1, and then we have the 6, r of t minus 2 becomes 6 times t minus 2, but we don't bring down anything else. And then as t continues past 3, it gets between 3 and 4. Okay, then all 4 of these first terms will turn on, but not the last one. So r of t again is t minus 4 times t minus 1 plus 6 times t minus 2 minus 4 times t minus 3. And then finally, when t gets past 4, we have all 5 terms contributing. So we'll have r of t is t minus 4 times t minus 1 plus 6 times t minus 2 minus 4 times t minus 3 plus t minus 4. And now all we have to do is simplify all of that. And since that's just pretty elementary algebra, I'll just leave that, and we get these expressions right here. Now, we don't know if that is correct or not, but let me tell you a way to sort of check it, okay? What I'm about to show you is a check. It doesn't guarantee you that your answer is right, but if the check doesn't work out, it does guarantee you that there's something wrong. So, and we've talked about this before. When you or we've talked about something similar to this before. When you integrate a function that is everywhere finite, you will end up getting a continuous function. If you have, what I mean here, just to make sure it's perfectly clear, we're integrating I guess it's not perfectly clear. What should I say here? Yeah, I guess it's not perfectly clear here that we're performing an integral. We're going to see in, in just the second part of this lecture that this answer could be obtained by integration. And so, that being the case, what we can say is that, well, let me just say we expect these terms unless, well, let me stop for a moment because I wanted to say this absolutely right. I guess there's no real easy way to say what I want to say. I'll just maybe say it this way. We very, very frequently will expect when we solve a problem like this to have continuity between the different regions. The only case where that will not happen is if the impulse response of the system goes to infinity somewhere, or the input to the system goes to infinity somewhere. Now, you can see that this input does not go to infinity anywhere. Now, we don't have the impulse response of the system, so we can't say that it's not going to infinity anywhere. But if you think about it, since this is the step response, the impulse response would just be the derivative of this, and the derivative is nowhere going to infinity. So in fact, the impulse response will not go to infinity anywhere. So that would be the way to say it. It's just that if you have a situation where the impulse response of the system doesn't blow up anywhere, it doesn't go to infinity anywhere, and the input does not go to infinity anywhere, and that will often be the case, by the way, then the response to that input will be continuous. And so that's what we're looking for here, is to check and see if this function, it has different definitions over different parts of the domain, but is it continuous? And the answer is, well, let's check. Okay, so for t less than 0, it's equal to 0. And then when we get into the range from 0 to 1, at the left-hand part of that range, at 0, this expression is equal to 0. So as we go to the right-hand part of this range, we have 0. At the left-hand part of this range, we have 0. So 0 is equal to 0, and we have continuity there. Now, what about when we get to the right-hand part of this range? Well, at the right-hand part of this range, t is equal to 1, so we have 1. What about the left-hand part of that range? T is equal to 1, and this expression would be minus 3 times 1 would be minus 3 plus 4, and that's 1. So, again, this expression and this expression agree where these two regions meet, which is at t equals 1. What about this expression and this expression? Do they agree at t equals 2? Well, at t equals 2, this would be minus 3 times 2 is minus 6 plus 4, so we'd have minus 2. And what about this one? At t equals 2, this would be 3 times 2 is 6, minus 8 that's negative 2 as well. So these two agree, these two expressions agree where these two regions meet. What about these two expressions at t equals 3? Well, at t equals 3, this is 3 times 3 is 9, minus 8 is 1, so we have 1. And what about this expression? Well, at t equals 3, it's minus 3 plus 4, and that's equal to 1. So once again, these two expressions agree where these two regions meet. And then finally, what about these two expressions where these two regions meet? Well, these two meet at t equals 4, and at t equals 4, this is minus 4 plus 4, so that's 0. And of course, this is 0. So everywhere these regions meet, the corresponding expressions do agree. So we have continuity, and as I said, that does not guarantee that this answer is right. But if continuity had not been preserved, then that tells you something is wrong. But fortunately, that did not happen, and so that gives us more confidence in this answer. And actually, what I'm going to do is in lecture 10, At the beginning of lecture 10, I will derive this result in another way. In fact, I'll probably derive it even in 2 different ways so that we can see for sure that it is correct. But before I can do that, we need to learn something more about how to find the response of a system to an arbitrary input, and that will be the second part of lecture 9. So we'll take just a brief break here, and then we will look at this lecture 9b. Okay, so as I said, lecture 9a was talking about old material, and we can say in lecture 8 we saw that the impulse response can be used to calculate the step response, and that the step response in turn can be used to find the ramp response. So that begins to show us why it's important to know the impulse response of a system. But in fact, the impulse response can be used, if you have knowledge of the impulse response, that can be used to find the response of the system to any input. And that's what we're going to see how to do in this lecture. And the way that's done is through something called convolution. So how does this go? So, okay, we have a system, we have some input X, and the output is Y, and we suppose that we know H. Remember, H is the impulse response of the system. Well, then, what we're learning today is that Y of t, the output, is equal to H convolved. This asterisk here means it's convolved. We're convolving these 2 signals. What does that mean? That means we integrate from negative infinity to infinity x of tau, h of t minus tau, d tau. And in case you're worried that you might forget that formula, well, you don't really have to worry because if you turned it around, that's true as well. This is the same thing as h of tau. So if you had the tau going with the h rather than with x, that's okay. Just remember that tau needs to go with one of them, and t minus tau is the argument of the other one. And both of those formulas are true. So what we will do now for the rest of this lecture is we will look at an example of this. We'll see how do you calculate this convolution integral, because it can be a little bit tricky with this t minus tau. See, tau is the variable of integration. So, you know, the argument of this function is getting bigger as tau gets bigger, but the argument of this function gets smaller as tau gets bigger. So that makes the convolution potentially a little confusing. So we have to be careful. So let's look at this example. If you go back to lecture 8, we found that the unit step response of a system whose impulse response is given by this is this. And just to remind you, we found that step response by integrating the impulse response. Okay, so now what I want to do is to try to solve this problem not by integrating the impulse response, but by looking at the convolution formula instead. So let me just make sure this is clear. Y step of t is the value of y of t when x of t is the step. So that means that for plugging in y step for y and plugging in u of t for x of t, so like I say, this is what we have right here. We're going to, h of t is the impulse response, y step is playing the role of y, and u of t will play the role of x. Okay? Now, we said that both of these convolution formulas would work. They should give us the same answer. So which one should we choose? Well, here's a rule for you that I think is the easiest, and we'll see how it works here, but we'll look at more cases in the future. But I think that it's easier to evaluate the convolution if you associate the more complicated argument, which is t minus tau. See, this argument is simple, tau, but t minus tau is a little more complicated. I like to associate the more complicated argument with a simpler function. So if x is simpler than h, I choose the first form, but if h is simpler than x, then I choose the second form. Now in this case, here's x and here's h. To me, x is a lot simpler than h, so I will choose this form. And actually, I'm going to show you how it works out both ways, but I feel like doing it this way is simpler. That's the way I'll do it first, and then I'll come back and do it this way. So let's see how it goes. So like I say, I'm first going to choose the form that associates the more complicated argument with the simpler function. Okay, so we have y step of t over here on the left, and here h of tau is this. And since x of t is equal to u of t, x of t minus tau will be u of t minus tau. Now, at this point, I suggest you pay really careful attention to the steps involved in evaluating this integral. So the first thing I'll do is I'll say that the upper limit on the integral, well, just look at this u of t minus tau that's sitting out here multiplying all of this. As tau increases, it will eventually, you should think of t for the moment as being like fixed. So as tau increases, it will eventually surpass t. And when tau does get bigger than t, then this argument will be negative, and u of a negative number is 0. So once tau gets bigger than t, we don't have any more contribution to the integral. So for the upper limit, we don't have to let tau go all the way to a positive infinity. We can instead stop at tau equals t. Okay. Now, over this whole range where tau is between negative infinity and t, the argument here is going to be positive, and u of a positive argument is 1. And so we don't really need to explicitly write u anymore. We can just take it out. Now that's this u. I'm not talking about the u that's inside the brackets. I'm talking about this u of t minus tau. So as long as we're between negative infinity and t, we know that as long as tau is between negative infinity and t, we know that u of t minus tau will be 1, and so we don't have to write it. So that's how we go from this step to this step. Now I'm going to break this up into two integrals. We'll have integral from negative infinity to t of delta of tau d tau, and then I'll for the second integral I'll pull the minus 6 out, and we have integral of negative infinity to t of e to the minus 3 tau u of tau d tau. Okay? Now, we know that the integral from negative infinity to t of delta of tau d tau is u of t. That's just automatic. That's something we've learned, and I hope that you feel comfortable with that. Just the integral of the delta function is u, integral of u is r. Okay, I'll put in this -6, and then for this integral, we'll look at two cases. If t is less than 0, then we're only integrating over negative values of tau, and so this u of tau would always be 0, and therefore the integral is 0. So if t is less than 0, this is 0. On the other hand, if t is greater than 0, we can say that we don't need to integrate over the negative values of tau, only over the positive values of tau, because again, over the negative values of tau, u of tau gives us 0. So instead of starting at negative infinity, we can start at 0. And over those positive values of tau, u of tau is 1, so we don't have to write it down. And then we just bring down the e to the minus 3 tau. And this is for t greater than 0. And so coming down to the next step, okay, u of t and -6 come down, the bracket, the 0 comes down, and when we integrate from 0 to t, e to the minus 3 tau d tau, we'll get a -1/3 on the outside and an e to the minus 3 tau here. Evaluate that from 0 to t. And so this coming down, the u of t comes down, -6, the bracket comes down, 0, the conditions come down, and then this just becomes -1/3 times e to the minus 3t minus 1. And now the way that we can write all this stuff in the brackets much more compactly is just to write it as minus, see this bracket, we have -1/3 e to the minus 3t minus 1 times u of t. That takes care of the fact that it's equal to that exactly when t is greater than 0, but it's equal to 0 when t is less than 0. Now we come down, we're almost done. The u of t comes down, -6 times -1/3 gives us a +2, and then we have the e to the minus 3t minus 1 and u of t. And now finally, if you write all of that out, okay, u of t, and then 2e to the minus 3t u of t minus 2 u of t. And then this u of t and the minus 2 u of t will combine to have minus u of t, and then the 2e to the minus 3t u of t is right there. And so we end up concluding that y step of t is 2e to the minus 3t u of t minus u of t, which of course is exactly the same result that we obtained using a totally different method before. We used the method y step of t. We just integrated the impulse response. There was no convolution at all. We just integrated the impulse response. Okay, so I think that you will agree that, oh yes, that required patience and it required that you be careful, but that was not too bad. So now remember, though, that there's an alternative way of expressing the convolution integral, and so let's see how that would go. So here we say, let's see how it goes if we use the second form of the convolution integral. In the second form, the more complicated argument is associated with h. So again now, x of t is u of t, so x of tau will be u of tau. H of t is delta of t minus 6e to the minus 3t u of t, so h of t minus tau becomes delta of t minus tau minus 6e to the minus 3 t minus tau u of t minus tau d tau. Okay, so let's see how this will go. Well, let's first of all think about this u of tau that's sitting out here multiplying everything. When tau is negative, that's just 0. And so the integral goes away. So therefore, we don't have to integrate over negative values of tau. We can start at tau equals 0. And then if we're integrating only over positive values of tau, then u of tau is always equal to 1, and we don't have to explicitly write it. So that's how we get from this line down to this line. Now, I'll go ahead and break up this integral into two parts. We'll have integral from 0 to infinity of delta of t minus tau d tau, and minus 6 integral from 0 to infinity e to the minus 3 t minus tau u of t minus tau d tau. Okay. Now, to evaluate this integral, I'm going to let alpha equal t minus tau. And so d alpha is minus d tau. And so let's see what happens then. At tau equals 0, since alpha is t minus tau, alpha will be t minus 0 or t. So the lower limit becomes t. At the upper limit, when tau is equal to infinity, alpha will be t minus infinity, and t minus infinity is still minus infinity. Since d alpha is negative d tau, that means d tau is negative d alpha. So the negative sign I'll bring out here out front, and then d alpha is in here. And since t minus tau is equal to alpha, then this just becomes delta of alpha. So the first term after the substitution, alpha equals t minus tau, this first term will become negative of the integral from t to negative infinity, delta of alpha d alpha. Now let's look for the second term. Okay, we bring down the negative 6. Now notice that this e to the minus 3 times t minus tau could be rewritten as e to the minus 3t times e to the 3 tau. And e to the minus 3t, as far as this integral over tau is concerned, e to the minus 3t is just a constant. So it can come outside of the integral. Now we can't bring out the side of the integral e to the 3 tau because we're integrating with respect to tau. So e to the 3 tau has to stay inside the integral, but the e to the minus 3t can come outside like this. Okay, so we're left inside, then we have the integral of 0 to infinity, e to the positive 3 tau, u of t minus tau d tau. Okay, and we're making progress. We're slowly but surely getting there. As we go to the next line, we're going to take this negative sign to flip the limits on the integral. So instead of negative the integral from t to negative infinity, it becomes positive the integral from negative infinity to t. And then we bring down the rest, delta of alpha d alpha. Now we bring down the minus 6e to the minus 3t, and then we're going to replace this integral by this bracketed expression so that we make sure to do everything correctly. And the way this will go is the following. Okay, we're going to, as usual, break it up into t less than 0 and t greater than 0, and let's see why we will do that. Okay, well, we have to think carefully about this u of t minus tau. Once tau gets to be greater than t, this doesn't contribute anymore, because then when tau is greater than t, the argument becomes negative and u of a negative number is 0. So if t lies somewhere in the range between 0 and infinity, we can say that some of the time this u function is equal to 1 and some of the time is equal to 0. But if t happens to be less than 0, then in this whole range of positive values of t, remember now we're thinking about t is less than 0. So t would be negative, and then if tau, since tau is in the positive range, negative tau would be negative. So we'd have negative t, we'd have t which is negative, negative tau which is negative. So all of this would be negative. So if t is less than 0, this argument is always going to be a negative number, and u of a negative number is 0. So if t is less than 0, this is 0. But on the other hand, if t lies, if t is greater than 0, if it's somewhere in this range from 0 to infinity, then we can say, okay, in that case, we do want to keep that part of the integration range where tau goes between 0 and t, because over that part of the range where tau is less than t, and we're assuming now that t is somewhere in here, so t is greater than 0, over that part of the range where tau is less than t, then this u of t minus tau is equal to 1. So we don't have to write it down here. Now, once we get past t, as we said, once tau gets past t, then the argument becomes negative, and u of a negative number is 0, so we don't have to worry about it anymore. So that's why we don't have to integrate past t, but we do need to integrate up to that point if t is a positive number. Okay, and then the e to the minus 3 tau just comes down, and we have d tau, and so now we're ready to, after all of that argument, we're just about ready to finish this problem. So we recognize this now as the integral of the delta function from negative infinity to t, that's u of t. And then we bring down the minus 6e to the minus 3t here. We bring down the 0 in the brackets. And finally, this integral 0 to t of e to the 3 tau d tau becomes 1/3 and 1/3 e to the 3 tau. And I've gone ahead and evaluated it from 0 to t. So we have 1/3 e to the 3t minus 1. And that's for t greater than 0. And now finally bring down the u of t and bring down the minus 6e to the minus 3t. And then all this bracketed expression can be just written as 1/3 e to the 3t minus 1 times u of t to, as usual, that takes care of the fact that it's equal to 1/3 e to the 3t minus 1 when t is greater than 0, and it's equal to 0 when t is less than 0. So this is what we have, and then 6 times 1/3 is 2. So we have u of t minus 2 times, and notice what we've done here, e to the minus 3t times e to the 3t gives us 1. E to the minus 3t times minus 1 gives us minus e to the minus 3t. And so we have this, and then if we multiply this all out and combine terms, notice we have a minus 2 times minus e to the minus 3t u of t, so that becomes positive 2 e to the minus 3t u of t. And then we have a u of t minus 2 u of t, so a minus u of t. So here's our final answer, which once again matches what we had above, right here. But I personally think that finding it using this first form of the convolution integral right here was a little bit simpler than what we did down here using this second form of the convolution integral. And again, that won't always be the case. It's just, I personally think it's easier when you associate the more complicated argument, t minus tau, with the simpler function. So if h is simpler, this would be the form I would choose. But since x was actually the simpler function in this case, I think that this is a little bit easier to evaluate. But anyway, that's our first two examples of evaluating a convolution integral. And don't don't be too concerned if it seems a little complicated. I mean, indeed, this is a new topic, and it is something that's sort of convoluted. And so, just take a look at it, and try to begin to get accustomed to it. We will look at more examples, and the good news is that we will also learn a graphical technique for doing this that will help to make some of this simpler. But anyway, so that concludes Lecture 9 of Electrical Engineering 331, and good luck.